Alright, hello, welcome back to another chemistry lesson here. We're talking today about energy in reactions. So, when you have an actual reaction happening, what is actually going on here? So, at the beginning, we're going to start here talking about collision theory. So, for a reaction to actually happen, the particles, the atoms, the molecules, whatever you're reacting, have to hit each other. The particles have to actually run into each other if you want a chemical reaction to occur. That makes sense, right? If they're not bumping into each other, how are they going to swap electrons, break some bonds, reform some bonds? It's just not going to happen. So they have to run into each other. Not only that, but they have to have the correct orientation to cause a chemical reaction to occur. So if they're not lined up right, they won't hit at the right angle to actually break the bonds and reform the bonds they need to do. So if they were to just bump against each other, you don't really have a reaction. Last one, something to think about here. Your concentration has a large effect on your reaction rate, which again kind of makes sense. If they have to run into each other at just the right angle for a reaction to occur, the more of them I have around, the higher the concentration, the more of them are going to be bumping into each other. And the more of them that are bumping into each other, the more likely they are to just randomly end up in the correct orientation for a chemical reaction to occur. So concentration ends up having a large effect on reaction rate. If you raise the concentration up, the reactions tend to go faster and faster. So one particle reacted with two particles, for example. So I've got, let's go for red or blue here. So here's a nice red atom, and it's looking to react with, let's call this oxygen. And it needs to react with hydrogens. We got two little hydrogens here. Now, I don't know if you guys recall, but water, H2O, generally forms this kind of a shape. And so if I've got these particles and they're bouncing all over and they're bouncing into each other, if these hydrogens hit here and here, that's not actually going to be the right angle in order for things to actually react or collide. Or if only one were to hit, and the other one were to miss, you're not going to make an OH, right? It's not going to happen. So in order for this to happen, the oxygen and the hydrogen have to bump into each other at roughly the same time, at roughly the right angle as well, in order for these bonds to actually form to make an oxygen stick to two hydrogens and actually do that electron trade, where the electron from the hydrogen shares one of the electrons from the oxygen. So if they're not at the right orientation, if they haven't run into each other, if they're not around, it's just not going to happen. So the more hydrogens I have, the more they're going to be bouncing against each other, the more likely it is that this reaction actually happens. But it's not enough just to bump into each other, right? If we're thinking about a chemical reaction like a car accident, for example, if they're moving slowly, the cars are just going to bounce off each other. It's not going to do the trick. But if you have a lot of energy, if the cars are moving really quickly, they will combine into some new monstrosity head-on collision car particle. So you need enough energy if you actually want the particles to interact. So particles must also have high enough kinetic energy, that's energy due to motion, so they can actually interact. If that hydrogen's moving too slowly, it's going to repel right off the oxygen there. And if it repels off the oxygen, it's not going to bind. I'm getting like a billion messages here. I'll check those later. So, low kinetic energy, the particles can't get close enough. Remember, if you look at what an atom looks like, you got a positive nucleus, and then you've got those negatively charged electrons in S and P shells all over the outside. But the next atom that wants to combine with this, if we're trying to force these two atoms together, looks the same way. It's got negatives around the outside. So those negatives are going to be repelling each other a bit. If you want those particles to get close to each other, you need to send them towards each other real fast. So they can get fast enough that the actual electron orbitals cross each other, they can start trading or sharing, and then you've got a bond formed. And so we call that activation energy. It's the minimum amount of kinetic energy for particles to actually collide effectively. If you don't have that much energy, particles are not going to collide effectively. So it kind of looks like this. This is a graph, you'll see a lot of graphs of a similar shape for reaction energy. Here's your reactants up here, and this is how much energy they have. So this is like high-ish energy. So the reactants are at this much energy. In order for them to actually react, I need to put in a certain amount of energy. So if this is where I end up here at products, we call the amount of energy required to actually do the reaction. Hold on, let me just... The amount of energy required to do the reaction is called your activation energy. The amount of energy required to actually activate this thing. Once you have that much energy, the different reactants can mix up here, and then they break their bonds, they form new bonds, and the amount of energy drops down here to the product level. Now, it doesn't always drop all the way down. Like in this case, the reactants had, let's say this is at 50 joules of energy. Now, if you look down here, we're at less. Let's just say that was 10 joules of energy. So you've lost energy. The reactants were up this spot. The products are now down here. So where did that energy go? Well, what this means is when we combine these reactants, they're going to end up giving off energy. There's a net drop in energy. And so that energy is released as heat. Which means this graph shows an exothermic reaction. We started with a certain amount of energy, and we lost energy. That energy had to be given off as heat, so it's an exothermic reaction. If you want to see what an endothermic reaction looks like, very similar graph, but you can tell now that the reactants are down here. There's the amount of energy required to actually react. But when you get to your products, it doesn't drop way below the reactants, it's up above. So the change in energy, the heat, it's actually in the other direction. I started out with some, I soaked a bunch up, and I didn't get all my energy back. So I soaked a bunch up, and I started getting some back, but not all of it. So I have to put energy into this. So this has heat absorbed. And of course, we call that an endothermic reaction. So, enthalpy. The term we use to figure out if it is exothermic or endothermic is enthalpy. And enthalpy is, the definition, the amount of energy associated with the system. So it's just how much energy does it have at a current time. We usually use the symbol H for enthalpy. Now, this includes both your potential and your kinetic energy, so it's how much motion there is happening. It's also how much potential is stored in the bonds, and it is measured in joules energy per mole. So if you have twice as many moles of reactants, you'll have twice as much energy stored there, which makes sense. So for a chemical reaction, you want to find the change in enthalpy. That'll tell you if you're endothermic or exothermic, how much energy has changed. Now, these are supposed to be subscripts, so it should look like H products minus H reactants. So you look at the enthalpy of your products, so the energy level of the products, subtract the energy level, the enthalpy, of the reactants. So enthalpy products minus enthalpy reactants tells you your change. If the change is positive, it means your products have more energy in them than your reactants do, which means you've stored energy. You're endothermic. If your enthalpy is negative, it means your products have less energy stored than your reactants. So where did that energy go? Well, it was just released, usually as heat. And so you have an exothermic reaction. So if you take a look here, for example, I know the energy of the forward reaction is 140. So this here is 140 kilojoules per mole. And I know my energy in the other direction is 100. Oh, no, that's my delta. I don't want my delta. This one. The energy in the reverse direction, so from here to here, is only 40 kilojoules per mole. So energy of the products, the total energy kind of taken up here, I've got 100, where are my products at? Well, I can say I used 140 kilojoules minus 40 kilojoules. So 100 kilojoules per mole is my overall energy change. So at 140, subtract 40, or I mean, sometimes they'll just tell you what energy level these things are at, and you can use that. In this case, I had to use the activation energy of the forward reaction and the activation energy of the reverse reaction to figure it out. But it's the same kind of idea. How much energy is soaked up or absorbed? You can subtract those things and figure out your overall change. And because this is positive, it's an endothermic reaction. There's one other part of this graph we haven't talked about much. It's called the activated complex. And that's right at the very top there. Let's use a different color so we can see it. At the very peak of the graph, that's where there is just enough energy to break those bonds holding the compounds together and reform new ones. So the activated complex is kind of where the bonds are re-breaking and remaking, and you get this Frankenstein of a particle. So if I was starting with this Nu with 2 electrons, plus whatever this hydrocarbon with bromine is on it, my activated complex is my transition state, happens at the activated, is also called an activated complex, and it's this Frankenstein of them. You can see I've got this dashed lines here. Those means partial bonds. They're partway breaking, partway forming, so it's kind of like a half molecule. At this point here, the transition state can go either way. So this activated complex can go either way. It could either fall down this way and form the products, or it could slide back and form reactants. They're kind of halfway forming. So if you have enough energy, it will slide down this way, and eventually you end up with 2 new products. So the Nu has attached, and the Br minus has separated with its electron now. So the activated complex, is the series of different transitions that can happen up here, and we call the transition state kind of this Frankenstein version of the reactants and products where they're halfway between and where it can fall in either direction. And catalysts. They also change what this graph looks like now. Let's use black for this one. So a catalyst speeds up reactions. We know this already. But the actual mechanism by what it does is by reducing activation energy. It allows molecules or atoms to bond easier. It allows them to line up better. It holds them in position so they can combine easier, which basically means they need less kinetic energy to actually combine. So it doesn't change your enthalpy. It doesn't change the heat of your reaction. Because if you look, my products are here, my reactants are there, my products are down there. It doesn't actually change where they start from. What it does change is, this is before catalyst, I needed that much energy. This is after catalyst, I only need that much energy. If you have less energy required, means a faster reaction. So things happen faster if you require less energy. And so that's kind of what a catalyst does to the energy pathways for reactions. And so that's all we got for today. Thanks for watching, guys, and we will catch you at the next lesson.